Hi grade 12s. We're now starting one of my favorite sections. It's a section on trigonometry. It's definitely one of the more challenging sections. It's part of paper 2. And so we're going to make sure that we do a lot of examples as we go, a lot of exercises, and definitely quite a few days of past paper questions at the end. It's a fairly long section, but it's such fun. I've divided into a couple of topics, and this video is on topic 1, which is kind of the whole point of grade 12, which is the idea of compound angle identities. Now, just quickly, what is a compound angle? A compound angle is an angle made up of 2 or more angles. So it could be more, but it's generally made up of 2. I'm going to say or more. And you'll see very quickly what I mean. Okay, now this video is basically just introduction to the various compound angles and the identities which we're going to derive from them, and then we'll kind of play around with them a bit, and then we'll start using them later on. So let's look at our first identity. Our first identity is the identity what would be the value of cos A minus B. So this is why it's called a compound angle, because the angle that you are taking the cos of is made up of 2 angles. Now, it's not distributable. So this is not the same as just saying, oh, so it's cos A minus cos B. Trig functions exactly the same with square roots. They're not distributable, so you can't do that. Please, please, please. It's actually a little bit more of a complicated formula. Now, all the compound angle identities are given to you on your formula sheet. And the original compound angle formula is this one. All the other compound angle formulas, which we're going to do in a moment, are derived from this compound angle formula. Now, the formula which we are about to derive, this derivation that I'm going to do with you is not examinable. So you do not have to study this, you do not have to know it, and you don't have to repeat it. It's just that if I show you the formula without giving you any explanation, it's kind of like, well, why? Why would it be that? So I'm going to talk you through where it would come about. So I've drawn myself a Cartesian plane, and I have labeled, well, I haven't labeled, but I'm going to call this angle B. So let's say that's an acute angle, angle B. And don't forget that all angles in the Cartesian plane are measured anti-clockwise from the x-axis. So that's going to be angle A. So if you're looking at A minus B, where is that physically? It's there on the Cartesian plane. So this is A minus B, because it's obviously the full angle, this full angle of A, and then I've taken away that angle there. And so that red part, that would be angle A minus B. So I'm trying to find the cos of that. Now at the moment I can't find the cos of that. It isn't part of a right angle triangle or anything. So what are we going to do? Well, there's a couple of steps that we need to do before we start working with A minus B. The first thing is to note that we're going to assume that we constructed both of these rays, as you call them, from the origin to Q, having a distance of 1 unit. So the R here is 1 unit, and the distance from the origin to P is 1 unit. Now, I mean, we're just the way we're going to derive it is using an R of 1. We could use an R of 2. We could use an R of 3. It'll always boil down to the same formula. So that's why it's easier just to use as 1. Now, we're going to drop a perpendicular down here, and eventually I will erase all of this mess. But basically, if I drop a perpendicular down there, I get a right angle triangle. This Q has an x coordinate and it has a y coordinate. This x coordinate would be this length there, and this y coordinate would be the height that Q is above the x-axis. Now I want to find out an expression for x, an expression for y using this angle of B. Now if you look for one moment, would you agree that if I said to you, what is the cos of angle B? Well, angle B is there, and cos is adjacent, which is x, over r, which is 1. Or I could have said cos, by definition in the Cartesian plane, is x over r, which is x over 1. So would you agree, therefore, that that 1 is, x divided by 1 is just x. So cos of B would work you out the x coordinate at Q. So if I write this coordinate in a different way, I could say that's cos B. And now the y coordinate, I can do a very similar thing, and I can say, well, sine of B, angle B, would be, well, sine is opposite, which is y over 1. Or you could say it's the definition of sine in the Cartesian plane is y over r, which is y over 1. So that's sine b equals y. So there we go. That's an expression for the coordinates of q. So q has a coordinate x, y, and you could calculate that x, y coordinate by doing cos of b and then sine of b. Now, there's no point in really doing this whole thing again. By exactly the same reasoning, this is cos of a and this is sine of a. By exactly the same reasoning. Now notice that a is an obtuse angle, and so when you cosed a, you would get a negative. Now that makes complete sense because this is a negative x value where p is. So the negative sign will actually be generated when you cosed the value of a. So why did I want to do this? I wanted to find a coordinate for q and p because if I go and construct a horizontal line between PQ, what I've formed now is I've formed a triangle. Now it's not a right angle triangle, but that doesn't really matter because in grade 11, I'm just going to make my pen a bit bigger so I can show you my triangle. In grade 11, we learned a whole bunch of trig rules that we could use in any triangle. So even though this isn't right angled, there's the cos rule, there's the area rule, and the sine rule that would now apply. So I can find the distance from P to Q by using my cos rule. So the cos rule says that PQ squared, the distance from P to Q, would be the other side squared, which is 1 squared, plus P to the origin squared. So that's these two values squared, minus 2 times the one side times the other side times cos angle in between. Now that's wonderful because if you have a look, this is ultimately what I'm trying to find an expression for. So if I neaten that up a bit, I get PQ squared is equal to 1 squared plus 1 squared is 2 minus 2 times cos A minus B. Now that hasn't really helped me because I'm trying to find an expression for cos A minus B, and this expression is lovely, but it involves PQ. So if I don't know the distance of PQ, then I can't really go any further. So now what we're going to do is we're going to say, and how else could you find the distance from P to Q? Well, I hope you remember that there's the distance formula. And the distance formula actually said, if I write it on the side here, distance is equal to the square root of x1 minus x2 squared plus y1 minus y2 squared. Now to avoid square roots because we don't like them, what I'm going to go and do is I'm going to square both sides. So instead of finding the distance from P to Q, I'm going to find the distance from P to Q squared. So the square root will then disappear. So then I have it's cos A minus cos B, because that's the difference between the two x values, and then sine A minus sine B. Of course I could have swapped those around because it doesn't matter. Now that is from your distance formula. So basically what I've done here is I've created an expression for PQ squared using my cos rule, and now I'm creating an expression for PQ squared using my distance rule. Now if I go and multiply this out, I get cos squared A, and I'm going to cut some corners and multiply it out quickly. So minus 2 cos A cos B plus cos squared B. So that was all the first bracket. Then the second bracket is sine squared A minus 2 sine A sine B plus sine squared B. Now wonderfully we have an identity that says cos squared A plus sine squared A is 1. So I get 1. Similarly, I have cos squared B plus sine squared B is 1. And then I have these two which don't have any like terms, so I'm going to keep them. So minus 2 cos A cos B minus 2 sine A sine B. Now why this is wonderful is that both of these two equations which I've kind of derived are expressions for PQ squared. So if I just use another color here, this is my first expression for PQ squared. So I could find PQ squared doing the cos rule and I'd get that. So that's my first expression. This is my second expression that I would find by using the distance formula. Now the reality is these PQ squares have to be equal because they're the same distance. So what I'm now going to argue is I'm going to say, well, but PQ squared has to equal PQ squared. And therefore these two expressions have to equal each other. So 2 minus 2 times cos A minus B has to equal, now 1 plus 1 over here is 2 minus 2 cos A cos B minus 2 sine A sine B. So all I've done is I've equated these two expressions. Now what's my ultimate goal here? My ultimate goal here is to get this by itself, because I want an expression for what that's equal to. Now wonderfully, if I have a 2 on this side and a 2 on that side, if I subtract 2 on both sides, those 2's actually cancel. So I get minus 2 times the cos of the compound angle, and then minus 2 cos A cos B minus 2 sine A sine B. So almost there. And so our last step is to realize that I can just divide every single term by negative 2. So finally I have my identity which I wanted to derive, which is the fact that cos A minus B is actually equal to cos A times cos B. So I always think of myself as cos the first angle, cos the second angle, minus, now it's actually a plus, I was just looking at that, it's definitely a plus, because I divided this by negative 2 and I divided this by negative 2, so it's actually plus sine A sine B. Now that's given to you on your formula sheet. This is what I wanted to derive. You do not know let me start that again. You do not have to know how to get to this, but it's very helpful to see, and it's a pretty nifty little proof there. So cos of A minus B, it's not distributable, the cos. It's actually equal to cos the first angle multiplied by cos the second angle plus sine the first angle times sine the second angle. Okay, so this is our first identity. So that's identity number 1. And there it is. I've written it up there. I've typed it up there. Simply because what they can ask you now is, can we use this identity to prove other identities? So there's actually 4 compound angle identities, because if you look at identity 2, what happens if it was cos A plus B? So what happens if this was a plus as opposed to being a minus? So what they can do in an exam is say, using this identity which is given to you, can you then prove the next identity? So now we do have to know how to do these next things off by heart. So what is cos of A plus B? Well, would you be happy with me saying that I could rewrite that as cos A minus? Now why do I want A minus? Because that's the formula I have. So I would have to say minus B. Now why have I done that? Because a minus and a minus make a plus. So this is equivalent, but I've done this because I know an identity for cos A minus something. And so now I can use my identity, because this is my first angle and this is my second angle. So now my identity says cos the first angle multiplied by cos the second angle plus sine the first angle times sine the second angle. I like to use first angle and second angle because otherwise the signs confuse me. Now this is easily simplifiable, because cos of a negative angle is the same thing as just cos of that angle. This negative sign doesn't make a difference, because you would actually then be in quadrant 4 and cos is positive. So cos of negative B is just cos B, but sine of a negative angle is actually negative sine angle. So this actually changes to a minus because of that. So this is minus sine A sine B. So this sine negative angle actually dictates the fact that that whole term is now negative. And so there we go, there's our next identity. Our next identity, also given to you on your formula sheet, says if you're cosing A plus B, it's equal to cos the first angle, cos the second angle, but now it's minus sine the first angle, sine the second angle. So very, very, very similar, obviously, but just a different sign. Okay, now a little bit more complicated is, can we use the identities of cos to help us find the identities of the sine compound angle? So let's have a look. What is sine of A plus B? Now, I know the identities for cos. I don't know the identities for sine. So can you rewrite sine using cos? And the answer is I can, because I can use co-ratios. So this would be, let me use a different bracket, this would be the same as cos of 90 minus a plus b. So I'm kind of like undoing reduction. If you think about reduction, if you're moving off 90 degrees in reduction, you would change the name to sine, and it would be sine of the angle. So I'm basically undoing reduction. I hope that makes sense, because this is quite a tricky step. So just look at this and try and convince yourself that if you had cos of 90 minus an angle, let me just write myself a note on the side here. If you had cos of 90 minus theta, for example, that would equal to sine of theta, because you're working off 90, so your name changes to sine. You are also in the first quadrant, and so everything's positive, so I don't have to worry about that. Now this is the same idea. There's the theta, and there's your theta. So if I'm working off 90, that would become sine of theta, which is sine of a plus b. So I've kind of like undone some reduction there, really. Now why have I done that? Because I have an identity for cos of an angle plus an angle and an angle minus an angle. Now I'm going to change this a little bit, because are you happy with me making this sine of 90 minus a as my first angle, so minus a, and then minus b as my second angle? So all I've done is I've kind of rearranged this, so it's 90 minus a as one angle, and then minus b as the second angle. So this is now my angle number 1, and this is now my angle number 2. But these two lines are equivalent. I've just kind of grouped things differently. Now why have I done that? Because the identity of cos angle number 1 minus angle number 2 is given to me. There it is. Cos of angle number 1 minus angle number 2. Now what does the identity say? It says you cos the first angle, which is cos of 90 minus a, multiply by cos the second angle, which is b. Notice the minus is just part of the formula, so the second angle is b. Now let's check what it says. It says cos the first angle times cos the second angle plus, so plus sine the first angle, so sine 90 minus a, times sine the second angle, so sine b. So now let's go and do some reduction here and neaten this up. So cos of 90 minus a, that is reduction, so 90 minus means the name changes to sine, so this is sine a times cos b. 90 minus changes the name to cos, so it's cos a sine b. And there's our next identity. If you're sining a plus b, it's sine the first angle cos the second plus cos the first sine the second. So this is different to the coses because they're changing ratio in each term. It's sine and cos, and then cos and sine. Okay, and lastly, I can now use that identity to try and get this one, because I can say that sine a minus b is sine of a plus negative b. I could also do this one using 90 minus and a cos, but if I've just done the previous one, I could say, right, this is sine the first angle, cos the second angle, plus, the identity said, cos the first angle times sine the second angle. So this actually becomes, don't forget that cos of a negative angle is just cos of that angle, but sine of a negative angle is minus sine of that angle, so that changes that sign. So again, very similar identities, exactly the same with the cos. The two cos identities are identical except for the sign in between the two terms, and the same thing is true here. Now, I could have proved this differently. It depends. If they asked me in an exam, they might have said, given you a cos identity. So if I needed to come from a cos identity to this, I could have said sine of a minus b is equal to cos of 90 minus a minus b, which is actually then cos of, if I group the 90 and the minus a together, and then the plus b. And now I can use the cos first angle plus second angle identity, and you will get straight back to that same thing. So if they ask it to you in an exam, they will always say to you, given this identity, can you now prove? So that tells you whether you're allowed to. You see here, I used the sine identity that I'd already derived. but they might give you the cos identity and say derive this, and so you always just pick which one you would like to do. Just to complete this identity says cos the first angle times cos the second minus sine the first angle sine the second. So that's the cos identity. Now cos of 90 minus a is sine a times cos b, and this is cos a because of co-ratios, and you get exactly the same identity. Right, so just to recap, there are 4 new identities. There they are. They're called your compound angle identities. They're all given to you on your formula sheet. You do not have to know how to derive the first one, but the subsequent identities you must be able to do from the given one. Okay, now what we need to do is we need to play around with them. So we need to look at examples of how does this help us, how can it be applied, etc. So let's look at a couple of examples. Now in these examples, what I've tried to do is I've put the identity next to it that you should go and look for. So this question, example 1, says simplify sine 40 cos 20 plus cos 40 sine 20. Now once you get really used to this, you start to realize that if the names are matching, so if it's cos sine sine, that's a cos compound angle. But if it's sine cos sine, so there's different names in each term, then I know it's in a sine identity. I then have to look for the sign here to tell me which identity it is. So it's a plus sign, and so if you go look at your identities, it's that one. So basically what they're saying here is that this is the first angle and that's the second angle, because it's sine of 40 cos of 20 plus cos of 40 sine of 20. So I know that this can collapse to sine of 40 plus 20. Now again, in my question I probably should have said without a calculator, because that's the whole point. Otherwise you could just put this on your calculator. So that's actually sine of 60 degrees, and sine of 60 degrees, you may use your calculator for that, because I won't know whether you cheated on your calculator or not, but technically that's a special angle, so we should know it's root 3 over 2. Okay, let's look at a couple of other ones. So cos of 3a times cos of 2a. So the moment I see it's cos, I think it's a cos identity. Now if there's a minus in between, I go look for that, and minus, and that actually makes it a plus. That's the identity. So basically this is the first angle. I'm not going to use a and b because it'll be confusing. That's the second angle, and there's the first angle and the second angle. So this is going to collapse to cos of angle number 1 plus angle number 2, which is cos of 5a, which I actually can't simplify because I don't know what 5a is. Okay, now I see I wrote b again, so let's correct that. This is c. Cos of 100 times cos 280. So immediately my mind's thinking, oh gosh, it's cos, so this is a cos identity. But if I look at my next term, you'll notice that that's a mixture. So this is an example of where I'm going to have to do a bit of work to make it fix one of the identities, which is why I haven't put an identity there, because it just depends on how you go and fix this. So let's have a look. I have 100 degrees and then I have 100 degrees. So those match. Now I have 280 degrees here and I have 350 there. Now those do not match, which means I need to make them match. So how can I rewrite 280 degrees, hopefully using an axis and an angle? Now I could rewrite 280 as 270 plus 10. We try to avoid working from 270 because then our name changes. I could write it as 180 plus 100. Maybe that would be a good idea. But ultimately, I wanted to get it to the same angle as that one. Now, how would you rewrite 350? I would probably rewrite 350 as 360 minus 10, which means it's going to reduce to an angle involving 10. So what this means is that I want to reduce this to an angle involving 10. So try and look at the combo. Don't just change one, because you actually want both of them to match. So now what I'm going to do is I'm going to say, right, this is cos 100 degrees, and this is actually cos of 270 plus 10. You don't have to write the step. You can go straight to the reduction if you want. And this is cos of 360 minus 10. I'm just writing it down because I think we're probably a bit rusty on reduction. So this is cos 100 multiplied by now 270. My name is going to change to sine. But what is my sign here, as in positive or negative? 270 plus 10 is in quadrant 4. and cos is positive in quadrant 4, so this changes to sine 10, minus sine 100 times cos of 360 minus, well 360 minus is in quadrant 4, so the sign is positive and the name stays the same. Now I can look for what identity it is, and this identity is a sine one because the names don't match in the terms. So this is angle 1 because it's sine of A minus B is equal to sine A times cos B, so this must be angle 2, minus cos A, so there's angle 1 times sine B, so that's angle 2. Now it really does matter who you decide who's 1 and 2, because what's going to happen here is this collapses to sine of angle 1 minus angle 2, so this actually becomes sine of negative 90. Now if you'd swapped that around and said that 100 was angle 1 because it just came first in the question, you would get 100 minus 10, which is 90. And sine of negative 90 is negative 1, and sine of 90 is 1. So it's very important that you assign the angle 1 and angle 2 according to the identity. If it says sine of the first angle, then whatever belongs to the sine must be angle number 1. I hope that makes a bit of sense. Okay, on to our next example. Should be example D. Sorry, my labeling was incorrect. Right, let's have a look. Sine 27, cos 33, sine 60. Oh, that's not good. Neither of these match. So can we rewrite them so that they do match? So let's have a look. Is there a way to rewrite 67? Well, it would have to be 90 minus. So this would have to be 90 minus, and it would be 27, which is good because it matches that. Can I rewrite 57? I can. It'll be 90 minus 33, which is good, so it matches that. So don't rewrite everything. Rewrite until you have a match. So actually this is going to become sine 27 degrees times cos of 33 degrees plus sine 90 minus 27. Again, you don't have to actually write the step. You can go straight to the reduction. 90 minus 33, which is sine of 27 times cos of 33 plus, now 90 minus is quadrant 1, so it'll be positive, but this will change to cos, and this will be positive again, but it'll change to sine. And so it's a classic sine identity, but it's sine angle 1, angle 2, angle 1, angle 2, and because this is a plus sign, this is sine of A plus B, if you go look at your identities. So actually this becomes sine of 27 plus 33, which is sine of 60. Now because it says without a calculator, it kind of makes sense that you'll end up with a special angle so that you can use special angles. Great, so this is a good way of just seeing how compound angle identities, how you can identify them and then use them to take a big sum and kind of collapse it down to something quite small. Okay, let's just have a quick look at example 2. Example 2 says prove that sine of 360 minus theta is sine of theta. Now that's actually not true, it's negative sine theta, so pardon my typo, there should be a negative there. Now we know that's true because of reduction, but this question says prove it's true. So how do we prove it's true? Well, there's an identity for sine of A minus B. So, and if I was you, I would really write those 4 identities on a piece of card that you keep next to yourself for all exercises, because it gets tiring remembering these things. So let's say this is angle A and this is angle B. And the identity said, if you look it up on your formula sheet, it said you sine the first angle, so that would be sine of 360. You cos the second angle, which is theta. You minus cos the first angle times sine the second angle. So sine of 360 is 0, so this becomes 0 times cos theta. Cos of 360 is 1, so it's minus 1 times sine theta, and so the first term disappears because it's 0, and you basically get minus sine theta. So that's a way to actually prove that reduction is true by using compound angle identities. Pretty nifty question. Okay, so that's topic 1. That's just an introduction to what are the identities, and just quickly a couple of examples of how to use them. We're going to be using them a lot in the topics to come, but this was just a bit of introduction into what they are and just cases where you can identify them.